The paths and elements may be the most exciting part of any K'NEX ball machine, but arguably the most important part is the lift mechanism. Today, that's what we're working on. The problem is straightforward. Automatically lift a K'NEX ball to the top of a track, and then do it over and over again. Over the years, there have been many solutions dreamed up by the K'NEX team and the K'NEX community. Mechanical arms, spinning wheels, telescoping tubes, ball launchers, elevators. They can be hand-cranked, motorized, wind-powered, even computer-controlled. By far the most common, however, is the classic chain lift. This lift was introduced in the Big Ball Factory set released in 1995 and has since powered thousands of K'NEX ball machines, from kits to original designs, and it is what I'll be using for this ball machine. This was not an easy decision to make. K'NEX chain lifts have a lot of issues, especially for a ball machine that needs to run 8 hours a day. The chain is prone to snapping, and the chain hooks can easily get jammed or break off. For my last machine at the works, I spent months designing a very over-engineered cable-driven computer-controlled ball lift specifically to avoid having to use a chain lift after my first installation's 23-foot tall chain kept snapping. However, the cable-driven lift came with its own set of problems. Though it failed far less frequently than the chain lift, when it did fail, the repairs were far more complex and time-consuming, requiring me to put in many hours rebuilding it over and over again. If I was unavailable, the machine would sometimes be down for days or even weeks, much to the disappointment of the guests. For this new machine, I gave myself a whole new set of requirements. Instead of trying to design a lift that supposedly can't fail, I need to embrace Murphy's Law and recognize that any lift design will fail sometimes, and instead try to design around what happens when it does fail. What if the machine could just keep running after a failure? What if it could be repaired by anyone in just a few minutes with just a bit of training? As for what type of lift, I know the staff at the works have experience repairing K'NEX chain lifts. My previous machine had 2 small chain lifts, which the staff frequently repaired themselves. A more complicated lift system would only make these repairs more difficult, so I'll be sticking with the chain lifts. But before I get any farther on the lifts, I need to shift gears a bit to work on another part of the machine. In the first episode of this series, I mentioned that I intended to reuse several elements from the old ball machine at the works. One of these elements is a large ferris wheel supported by 6 spokes. This element needs a lot of space to spin freely, so I'm going to install it now to make sure I don't accidentally block it off while working on something else. The other thing the wheel needs is a pair of sturdy supports on either side to hold the axle. It'll be easy enough to attach it to the back wall of the machine, but how do I support the other end? A large vertical pillar is the obvious answer, but there's only the sloped floor beneath it which can't support much weight. Instead, I'm going to run the pillar all the way through the floor, connected to a crossbar on the underside of the machine. A set of tension rods will help the crossbar carry the weight of the pillar, and 2 more vertical supports will distribute the load to the sturdy outer frame of the machine. This is where I'm really glad to be using a modular design. I can simply remove the middle section for easy access to the framework at the bottom. If this was built all as one machine, adding an interior support this late into the project would be a nightmare. With the support ready, I dusted off the wheel in my garage, inadvertently turning it into a giant spinning top in the process. When I brought the wheel back inside, I realized I somehow managed to build the support 6 inches too far out from the back wall, so I had to go back and start over. You may have noticed that the wheel makes this section far too wide to fit through any of my doors now. When it comes time to move the machine, I will have to disassemble the wheel temporarily, leaving only the hub installed. With the wheel securely in place, we can finally get back to building the lifts. Finishing the gearboxes is pretty straightforward. It's just a matter of building copies of the gearbox I made for the last episode, then installing the whole assembly back at the top of the machine and adding the chain loops. With the lift now running at full capacity, I decided to let it run for a while to make sure everything was working, And it all went great until Orion started climbing up the back wall of the machine to get a better look. We spent a few minutes trying to get him down as he walked back and forth across the beams, but eventually he jumped down on his own. However, the intense vibrations caused the third lift to jam against the mesh cage, but the friction gears did their job and prevented any damage to the motor or gearbox. All in all, a successful test. So before we start building all the various paths and elements that will make up the machine, we need a way to route the balls onto multiple unique paths, and in this machine, this poses a few unique challenges. How can I divide the output of 3 lifts into 10 or more paths using as little vertical space as possible? There are many path separator designs out there, but one of the simplest and most common is the 2-way rocker switch. They're quite reliable, but a ball loses about 3 inches of elevation each time it passes through one. To separate the balls into at least 10 paths would lose an entire foot of elevation before the paths can even start. On the previous ball machine, this didn't matter. That machine was 24 feet tall, so losing a few inches here and there was trivial. In this machine, however, only 5.5 feet separate the top of the lift from the sloped floor, and I want to make sure as much of that space as possible is dedicated to ball tracks. To do this, I'm going to try building a pegboard with a gentle slope. Balls will enter at the top from the 3 lifts and randomly bounce through to the bottom where they will exit into 10 different slots. Some of you may already see the potential problem with this design, which is that the frequency of the balls may tend to follow a binomial distribution, with the balls being biased towards the middle paths and fewer balls taking the paths at the edges. While this is true, it's something that I feel I can actually use to my advantage. The more common paths can be routed to more visually interesting or reliable elements, or run through additional path separators to make even more paths. Less common paths can be routed to elements that need a lower frequency, like gravity-powered ball arms. But the only way to know for sure how even it will be is to build and test it. I was just getting started on the pegboard when a package showed up at my door. I opened it up to find that an anonymous viewer had just donated over 3,000 white rods to help me finish this project, and the Works Museum and I are very grateful. This will be plenty to allow me to finish this machine without having to compromise on the design. With this fresh supply of white rods, I'm able to build the pegboard using a white connector floor structure, but rotated 45 degrees, so the balls will follow the white rods and have a smoother rolling surface. I then installed it in the machine using a box truss to hold it at a slight downward slope. Right away, I noticed an issue. The pegboard is quite heavy, and it leans toward its unsupported corner. This could bias the balls toward one side. So I decided to add another support pillar in the middle with a diagonal brace to hold up the pegboard, as well as a matching brace on the other side of the machine. After quickly constructing what is quite possibly the most boring ball track in history, the lifts and pegboard can now be thoroughly tested. One of the most critical things to test at this point is the ball divider at the bottom of the lifts. This ball divider will automatically split balls between the 3 lifts and hopefully automatically reroute them around lifts which have failed. With 3 lifts, there are 6 unique failure modes where at least one lift continues running, all of which will be tested. We'll start with the normal condition of all 3 lifts running. Since this is looking good, we'll shut down the first lift now. The divider is still working fine, so we'll turn this lift back on and shut down the second lift. This mode actually seems to be jamming pretty badly, so this is going to need some trial and error of adjusting the dividing walls until it all seems to be working properly. Now that everything seems to be moving smoothly again, we can shut down lift 3 and turn lift 2 back on. And again, things are running smoothly. Just to be safe, because I did modify the design a bit, I will retest with lift 1 shut down to confirm that this failure mode still works. Now we'll try the double failure modes, starting with lifts 2 and 3 out. So far so good. Now lifts 1 and 3 out. And finally, lifts 1 and 2. It seems like all failure modes are running just fine for now. Longer and more robust testing with further adjustments will definitely be needed in the future, but for now this shows that the concept works well enough. I am still concerned by the amount of sag in the top crossbar though. Even with the extra bracing, it's still causing the pegboard to slope a bit to one side. In an attempt to solve this once and for all, I'm employing the same solution I used with my most recent ball machine, Pandemonium. In order to span the entire width of my old living room, I pre-stressed the box trusses by running tension cables underneath them, reversing their natural curvature and allowing the trusses to rest perfectly flat when under load. Using a special Connex piece known as a rod lock, which increases the amount of tension a Connex connection can hold, I ran a pair of tension cables under the crossbar with 2 short vertical supports to push it perfectly level. You can see the difference here, and while it may not look like much, it's enough to level out the pegboard. Now before I get too much further, it's a good idea to do another test to make sure the sections can still fit through my door and up the stairs. The section on the right is the largest, so I'll test with that one. After some unexpected difficulty maneuvering it around a low-hanging light fixture, it just barely squeezes through the door and onto the stairs. The last thing I'll do for now is install a few triangular ball diverters in front of the vertical pillars, so balls landing on the floor behind them won't get stuck. And that's it for this episode. Stay tuned for next time when we'll start building the paths and elements for the ball machine. As always, thank you for watching.